Is there something about this morning you would like to discuss? Question or complement something? No? So I'm actually almost done. It's just a few slides left. It can be useful to just have heard about these things, splitting methods. And what I explained before around the first order methods, you can frame these things in this splitting context. It's just a way of looking at these things from a different point of view. When you discuss about splitting methods, what people have in mind is problems in this form. And it turns out that you can put many problems in this form, like MPC and so on. So here is the deal. You would have two sets of variables, w's and y's, and you optimize over both. And you have two functions, you sum them up, phi and g. And then you have some coupling between these two things. What would typically happen, what people have in mind when they do that is you have typically a smooth function here, your phi, that can be your normal cost function, and your g may be any function including functions that can take infinite values when you violate constraints. So the idea behind this could be that phi is your normal cost, and g could be something like this. All right, so something that would be called an indicator function. So if your y is in the correct set, it would return 0. If it's outside of the correct set, it would return 0. If you're trying to minimize the problem over this. Well, that's an easy way of saying you don't want to be there. Put an infinite penalty. It's actually, don't be surprised by this when you play with dynamic programming or stochastic dynamic programming. You use these kind of things all the time to typically represent constraints by infinite. And mathematically speaking, there is no problem with doing that.
Numerically speaking?
Well, numerically you don't want, of course. But that's one way of building things. Then numerically you do something different. Or you don't do something different. You account for that in the proper way, typically by actually putting constraints. Yeah, it has some consequences when you do stochastic optimization because you need to treat that in the context of measure theory. But that's another question. Yeah. We'll assume convexity here, but G is not necessarily smooth and is typically used to treat inequality constraints. That's one way of thinking about these questions. And then you can still build things around this. So you can build a Lagrange function. You would dualize these constraints, for example, and essentially you end up with a problem that has no constraints at all. It's only a cost with normal cost, something that goes to infinity when you violate constraints, and then a dualized set of coupling constraints. Dual function. You can, so it's basically minus mean of your Lagrange function, no constraints. And you can write it as a sum of somehow a dual function associated to phi and one to g. Because you can basically decompose this thing in two parts and have one function based on w and one function based on y. So you have the lambda transpose CW part that builds one dual problem, and the G lambda transpose y that builds a second dual problem. So when you do this, you can split between minimizing that part and that part, right? That's the splitting in some sense. Then the usual stuff. It does not matter that G may possibly take infinite values. All this construction and the dual function and everything is still well defined and works. So you would solve the dual problem that is made of the sum of these two things. So when you do min of the dual function, you basically need to minimize over these two functions summed up. Then how do we treat the fact that G may jump to infinity? You cannot apply gradient methods or anything like this. So to treat that, you need to introduce the proximal operator, but not for sets. If you remember, for sets, it was like basically find the closest point that is in the set. If you work with functions, it's a slightly different definition. You minimize, so if you do the prox over phi, you minimize over the function phi the x that is as close as possible to the y. So y is provided, and you would basically do a compromise between departing from y and minimizing x. If this function is an indicator function, like takes 0 value when you're in the set and infinite values outside, this actually matches the prox operator on sets. So you're essentially doing the same thing. You can actually easily imagine that. If I have some set S and I define my function phi as 0 if x is in the set and infinity otherwise. Right, so it's 0 in here and infinity otherwise. And you apply this kind of operator for example, a point that is outside the set. Then you don't want to leave the set because it would return an infinite penalty. So this term would be unacceptable. So you have to be inside the set, then this term returns 0, and then you minimize the distance to y. So you would basically want to go as close as possible to y while staying inside the set, right? And then you have the notion of proximal gradient steps as well. It looks the same as before. We will just basically apply the prox operator on this function, the dual function of G, this guy that can return infinite values, and we use a classic gradient step. And you have a 1 over L here that's nothing to worry about. It's just to things up in what happens at the end. There's a way of understanding what the dual step does. We'll basically seek, so the x does not match the primal variable here, it's just the support variable for minimizing. But it matches solving a problem that compromises between the dual function of G and taking some x or some value that is as close as possible to what the gradient step would want to do. In some sense, essentially take the gradient step on lambda and then try to find a lambda that is as close as possible to what you want here, but does not make this function explode by leaving the feasible set. There is one interpretation of what's happening here, which is essentially saying that what we do here is we basically take some kind of quadratic model of the dual function on phi. So you have the function, a linear term that approximates the function by its tangent predictor in some sense, and a second order term that does not use the gradient of the dual function but replaces it via this quadratic term. So if your dual function was basically a purely quadratic, this would be an exact term. And then you use the exact dual function dg. So you try to find the lambda plus that is good in sense of this quadratic model, and that is minimum in sense of the exact function dg. Okay, that's a little bit abstract, so if we try to use that on some quadratic problem or program, it may actually help a bit. So here is one example. So will be a simple credit cost and some bounds on W. And here is one way of splitting the problem. So you need a function phi w g of y and possibly some equality constraint. So here's a possible choice. This would be your normal cost. You call it phi of w. And then you create this indicator function that becomes infinity when y leaves this bounds, right? So that's this I of this guy here. That's one way of noting a function that takes infinite values when the constraints are not satisfied. And that takes 0 value otherwise. Evaluate on y, and then you basically make a copy. You say y should be w, okay? So that's one way of putting this MPC problem in this splitting form. Does it make sense? No? So in principle, mathematically, obviously, if you solve this problem for w, there should be y as well here, and we solve for y is part of the decision variables. Y has to be like w, and y cannot leave the feasible domain, otherwise this becomes infinitely expensive. So it's kind of obvious that this problem is supposed to match that one. But then you basically do this construction. So you dualize this copy constraint if you want. And then you have to work on your dual functions. But that's where things will tend to become explicit when you do these things. So your dual function for g, it's basically this g minus lambda transpose y. You can obviously also reframe that as this is a cost to minimize, and you want this one to not be infinity. So you want the variable to be within the bounds. So it's actually a simple linear program in that sense with this bounds. And this guy has an explicit solution actually for this simple bounds. You can imagine in some sense that these bounds are creating a box, and the lambda is a pointer in some specific direction. So essentially, if your lambda wants to bring your solution here, you will tend to move here and then in the corner, right? So you can basically very easily identify what x is minimizing this linear program. And the dual function for different lambda ends up looking like something like this, like a piecewise linear function. So this dual function is is like completely inexpensive to evaluate. And the dual function for phi, it's essentially only this part with the contribution from the dualized constraint. So it's a simple quadratic function, right? And that takes a simple solution. It's like basically h minus 1 f plus lambda, right? You're just minimizing a quadratic cost function. And if that's not completely obvious, but if you work out the gradient of that function, you end up with minus w. Or it's obvious if you remember that when you dualize a constraint, the gradient of the dual function is the constraint itself. So in that case, it's your w. So then if you take a gradient step on lambda for the dual function of phi, so we basically just follow the gradient. So lambda plus 1 over L w. And then you take a prox step on this based on the function dg. And so it's essentially trying to find the lambda as close as possible to the lambda that the dual function of phi would like to have while respecting the constraint. So essentially, this problem, you can solve it explicitly because of what we mentioned before. So essentially, when you solve this QP in this form using the splitting method, you have very simple linear systems that gives you W. The steps are completely obvious, and you take prox steps that are completely inexpensive. So So it's probably a bit fast. You want to work that out offline if you're interested. It's also best to actually code these things. It's completely trivial to code these guys. It's a few lines of code, and you probably see how it works. Okay, but that was a little bit easy again. That's a simple QP with without equality constraints. If you have equality constraints, it's a little bit less obvious. So when you have an MPC problem, for example, you would have the dynamics coming in, typically something like this. And if you have box constraints, that's always ideal. So how do you go from a QP that could be an MPC problem to the split form? And it's not obvious. You have actually two main approaches. You essentially have to decide what is the feasible sets that will generate the function g. And one choice is the same as before. You will choose the violation of the bounds as your g function. So you basically put an infinite penalty in the cost for violating the bounds. So in that sense, your g function would be in that form. So what happens here is essentially you end up with one function, phi, which will treat... wait a second. No, it's the other way around. Sorry about that. So you create one function that cares about the cost and staying within the bounds. So this phi function will basically ignore the dynamics. It will ignore that constraint. And you can view this part alone as a QP with quadratic costs and some bounds. And that's typically easy to solve. And the part that you put in a g function is the dynamics. So you would pick your g function as this, and the C matrix we saw before would be this D matrix. Yeah, that goes that way. So you can think of phi as solving a QP that ignores the dynamics. And then this G function will basically try to pull your solution on the dynamic constraints. The second split is the other way around. So in that case, the G function is about violating the feasible domain, the bounds. So then you have something that is very much like before. And the phi function will take care of the cost and the dynamics. So that will be a QP problem without inequality constraints. And there you have the same prox operators as we had before. So in that case, you have one problem that ignores the bounds as opposed to ignoring the dynamics, and one problem that's, that pulls the solution inside the bounds. So you end up with the two splits, the one for the dynamics. So we have this. So phi takes care of the cost and the bounds, and G takes care of the dynamics. So you end up with solving this problem here. That's basically a QP that does not have equality constraints. It's ignoring the dynamics. And the prox step will basically enforce the dynamics by taking steps on the lambdas that will bring this to 0, and that's the dynamic constraints. This is actually, we actually saw this type of algorithm before. That's this dual decomposition on the MPC problem using the prox steps on the dynamics. So that was in some slides before. So that's one way of understanding what happens there. And the second approach, so it's you create one problem that ignores the constraints and only takes care of the cost and dynamics. So that will be an unconstrained MPC scheme, this one. And the G function takes care of the bounds. So the phi function is essentially a QP problem without inequality constraints. And then the proc step, as we saw, it has an explicit form if you have simple bounds. Yeah, okay, that was more or less the idea here. So that's a wrap up for this lecture. So all these decomposition and splitting methods are used a lot in optimal control and MPC. You can do a number of things, ranging from accelerating codes or actually writing codes that you can implement on the most basic CPU ever, because you can skip completely doing linear algebra using these splitting techniques. First order methods are used a lot. A lot of people are working on them for a number of reasons. The price to pay for using these things is that it's often not, it's often iteration intensive. So you do very little computations in the iterations, but then you end up doing a lot of iterations. And another approach is to use second order methods, but then you have to be a bit careful with the non-smoothness of the functions. Yeah, remember, if you do MPC with simple bounds, there's a number of things that can be done to simplify the codes. And if you have a diagonal weight on your states and inputs, then you can make that extremely simple. So if you can fit your problem in that context, then it's golden. You should use it. And yeah, the splitting method, that's a generic way of thinking about all these first order splits that we have looked at, and all these proximal gradient methods. Okay, and with that, we're done with this course. We can discuss your projects a bit if you want, if you have questions on formulations and how to proceed. Yeah, and otherwise, that's it. Thank you for your attention.